Hi, my name is Brad Frieden. I'm a product marketing engineer at Agilent Technologies. I'd like to take a few minutes to show you how a logic analyzer with high-speed timing capture combined with deep memory can help find the root cause of a failure in a system. Today we're working with a design that's implemented in a Xilinx Zinc 7000 series, and this device is trying to send data out, but it's not making it to the other device. And we need to find out why. So we have taken a 16850 series logic analyzer, we've attached it to the device under test using single-ended flying lead probes, and we're going to look closer at what's happening in this design. It should be sending out a 5-bit state machine that runs it through the paces of sending out the data, and each time it sends out the data, it should get an acknowledge signal back saying, send more. But something's gone wrong. So we're going to look carefully at the signals and see if we can find the root cause of failure.
If we go to the main logic analyzer interface and select the bus signal setup tab, you'll see that I have defined a number of labels like state machine and assigned logic analyzer channels 0 through 4 from pod 1 to that label. I've also defined a single bit clock, and I've defined the acknowledge bit and the timeout bit. Then in the sampling window, I choose between timing capture and state capture. State capture is where I would trigger and then have samples captured on the clock of the device under test. I'm going to choose the timing capture mode, where the logic analyzer creates the clocking, and typically you do that much faster than the clock rate of your device under test, so you can see some detail of what's happening. And in fact, I'm going to choose the half channel 5 GHz mode so that I have very high resolution combined with deep memory. I've chosen 4 megasamples of depth, and I've placed the trigger out near the end of the capture so that I can look back in time from the trigger point to see what's happening. If we select the waveform window, you'll see that these buses and signals have been set up here. And I'm going to select a trigger condition for the rising edge of the timeout signal. If I press run, I see that I did in fact have the target pull the timeout flag. I triggered on it. The acknowledge line, there's no activity. I see the clock, and the state machine is stuck at a 1F invalid state. I can select zoom out full and look back almost 500 microseconds and see there's a burst of activity. Here's the state machine, here's the acknowledge line, and I can now zoom in to see what is happening in this design. I see a burst of the state machine with an acknowledge, a second burst and an acknowledge, a third burst, and now something's gone wrong. No acknowledge signals coming back. But if I zoom in here and look closer at what's happening, I can see this one hot state machine walking through its states: idle state, start state, address state, data, and wait for acknowledge state. That looks right. But if I look closer, I'll see that the rising edge of the clock, it is not centered on the data as it should be. In fact, it's time coincident with the changes in the state machine data. And it turns out this design did have a mistake in it. The user constraint file was not set for the Xilinx Zinc 7020 design, thus causing the clock to line up with the transitions in the data. We've found the root cause of failure.
I think you've seen how high-speed timing capture, and in this case 5 GHz, combined with deep memory, allowed us to trigger on a symptom, which was a timeout flag, and then look way back in time to the point where there was a root cause of failure. And in this case, there was no functional problem with that state machine, but there was a timing problem between the clock and the data bits of that state machine. Thanks for your attendance. If you'd like more information, you can go to the URL on your screen.